Hello! This is my particle system. What we're trying to do here is create a series of bubbles that are able to coalesce, able to split apart, and most importantly, when they hit the bottom of the floor, they pop. In addition to this, we also have gravity and friction, which influence the bubbles in their own ways. If we inspect the motion of the bubbles further, we can see how they warp around each other. In this red bubble, we're tracking and recording data for. See, it's falling vertically and now it's attracted to these other bubbles. See, the motion becomes a lot more varied, and you can see how this results in the outer shell wobbling like a bubble would. To implement this in code, we're doing something similar to what planets may do in real life. We have a gravitational constant g and the distance squared, and then using Newton's law of universal gravitation, we have a formula which will calculate the force of attraction between these two particles. We're assuming that particles have a mass of 1, which results in the strength of the force being equivalent to g over distance squared. This, in its essence, is what produces the undulation that we see. We have a small constraint here, which just avoids a divide by zero situation, and we have a negative multiplier, which allows particles to essentially bounce off each other when they get too close. This means that when they're within a threshold distance, they can come together, and if they're too close, they kind of bounce back with a slight damping effect. So that's why it's only negative 0.9 and negative instead of negative 1. In our actual particle system, when we update every particle, we first check if the distance between two particles is within a threshold, and that's only when they're attracted to each other. We also have gravity and friction, gravity being of a constant strength, and friction being a function of the particle's velocity. We multiply these both by modifiers, which are part of the GUI, and then apply the force to the particle itself. Finally, we update the particle. We add the acceleration to the velocity, we limit the velocity, and then we add the velocity to the position. We finally apply a 0.8 multiplier to the acceleration. This gives the bubble a bit of inertia and allows this force to slightly drain out instead of instantly vanishing. If the particle is against the wall or against the roof, it bounces back, but if it is hitting the floor, it will pop. Now if we jump back to the data that we recorded earlier for this red particle, we've laid it out in a Jupyter notebook. Here we've imported it as a CSV file, loaded it into a data frame with pandas, and then we can start displaying the data. So you can see how the acceleration, it starts off quite high as it exits the generator, and a little peak in its velocity. You see a slight attraction to another particle and has a slight increase in acceleration. Then as we go along, this is where the particle is falling down vertically. You see it meets another particle, and we have this influence of acceleration going higher and lower as the particles get closer and further apart. This is the undulation that we're seeing. We're also seeing this in the velocity, as that is also varying. Here we can see the position data. So as gravity is constantly in effect, the z-axis moves in a straight line with no other influences, and we have this undulation where we see the particle still in a downwards trend. The x and y, as it comes out of the generator, you see this little movement, and vertical down there's no horizontal movement, and again this undulation. This has been mapped into 3D, where the thickness of the line represents the velocity. It's interesting to note where there's no influence by other particles, the velocity is constant. This is the blue region where there's no attraction. This is because the friction and gravity forces are balanced out, resulting in an equilibrium and thus a constant velocity. And this is how it all works under the hood. We have a 3D field of points, which are the vertices of the cubes. We then draw triangles between the edges of these vertices, depending on the state of what the vertex is. If you have a bug in your code, it will look something like this. But otherwise, if everything's done correctly, it should look like this. We can then apply linear interpolation to this to make everything a little bit smoother. Since everything is done independently of each other, we can put the calculation for the mesh in a thread. This allows the processor to do 8 times the work it could have done, as we have 8 cores. For a similar reason, calculating the mesh that surrounds the particles is done in a similar manner using threading. This results in a much more efficient approach, and both of these algorithms can be ported onto the GPU, and even with some vertex shaders to provide a more transparent look to the bubbles. Now let's have a look at some environment variables. Our two that we have here are gravity and friction. If we increase gravity, we can see that the particles will fall a lot faster. If we reduce that again, they start to fall slower, until we hit the point at which gravity is less than friction. If we do that, then the force acting downwards on the particles is not able to overcome the friction. Therefore, these particles will still wobble about because there's still interaction between the two particles, but there is no general downwards movement. Then if we increase the friction, you can see that the particles stop moving, and two, the way that the particles kind of interact with each other, there's a significant decrease in their speed and how fast they come together. Now, if we take a look at the particle variables, we have this first one called attraction distance. This means that a particle further away will be attracted to another one at a further distance. Bring that up, we can see all these particles come together that weren't coming together before because the range is now larger. It's easier to see if we put it in the particle mode. Here you can see all the particles coming together, and the ones that are far away are all coming towards the central mass. Here is the skin again, and then if we drop that right down, see all these particles are no longer attracted to each other and will just fall to the ground as if their neighbours don't exist. And finally, the velocity limit. If we increase that, the particles start to move a bit faster. And you can see that as these particles come towards each other, they have a higher top speed, and so they move towards each other faster. If we drop a 0, obviously nothing's going to move. When looking at the performance of the system and the algorithm itself, we've got these two variables. So field resolution is our key one. This describes how many cubes we can fit in our entire box. We decide how many rows, columns and aisles we need by dividing the box size by this resolution value. So if we bring this all the way up, we have these really pixely values. So you can see here that we've got quite a few particles, but some of them just kind of pop in and out of existence as they move through the cube. So the resolution just isn't there to support any realistic rendering. Now if we drop this all the way down to a value like 4, we've suddenly got a very poor performance. This is because the number of cubes has increased exponentially with the resolution increasing. Therefore, the process is having to do many more times the processing than it did before. You see under the hood, see how many more dots and how many more cubes the processor has to look at for each frame to decide the influence of the particle on the mesh and where the mesh should lie. I've recorded the frame rate at different resolutions over a period of 1 minute. You can see at a high resolution with a value of 4, the frame rate starts at below 20 and ends up at around 4. At 6, it starts at a decent value at 50, but then ends up again below 10 You see this increases until we hit our frame limit of 60 FPS, where resolution of 10 and 12 line kind of fluctuate about. The lines with a higher resolution are shorter because the number of frames that they compute within a minute is significantly less, as you can see by both the FPS listed and the length of the line themselves. A similar thing happens when we increase the number of particles. So we currently have quite a few here, and if we just let these increase, you can start to see our frame rate drop. I've recorded some more data, this time relating to how the frame rate drops dependent on the number of particles that exist in the system. As you can see, we hit our frame cap at the start between frame 0 and 1000. That's where the particles are only around 40 at most. Then as the particles increase, you can see that the frame rate just drops. It goes from 60 all the way down to 4 FPS. This experiment is run over the period of 3 minutes, and as we reach around 260 particles, our frame rate drops to around 4 FPS. We're not seeing any transfer of data between the CPU and GPU because we haven't implemented any rendering on the GPU. It's all CPU based inside the threads. We also have a variable called mesh size. This has less of an impact on the time it takes to render a frame, as the only change here is the number of triangles that we have to draw. By changing this variable, we're just changing the area of influence around the particle. So if we increase it, we have a larger area of influence, so the mesh is larger. And then if we decrease it, we can see that the mesh size shrinks dramatically until the particles become barely visible. And this concludes my particle system. As you can see, the bubbles follow real-world physics as shown earlier. They wobble, they undulate, and they push up against the side of the box as a bubble would, and they pop when they hit the floor. The next step of developing this were to add a vertex shader and a vertex computes module to the GPU, which would mean that all cubes are independently processed. And then with the shader, we can add a more realistic texture to the bubble. Thank you and goodbye. Why won't you work?